In the line stuff, so the line, we're dealing with arrows on both ends. A ray has arrows on one end, and then a starting point or a termination point, depending on which direction you're looking there, that you go from. So when you name a ray, you always start with that point and then go away from it in the direction of the ray. So when you're naming a ray, whatever letter is here to name that point, that's the letter you have to start with when you're naming a ray. With a line, when you're naming it, it doesn't matter what order you put your letters in. There's no correct or incorrect way. As long as those points are on that line, you're good. With a ray, it does matter what order you're putting in. And when you're naming a ray, you're going to put that picture above it, the picture of a ray above your name for that particular ray. Angles are made up of two rays, and then that vertex is the corner. The vertex of an angle is the corner. When we talk about polygons later on, the vertex or vertices is the plural for that. Those are going to be the corners that we're dealing with. When we talk about segments, and I don't think I had a box about segments. Segments are dots on each end, no arrows. Okay, so when you talk about a segment, it has an ending point and a starting point, so one on each end. No arrows when you're talking about segments. So we'll talk about that a little bit as we go along here. And then, so notation-wise, we're going to kind of have to do some adjustments. My little pictures above the things did not turn out as I had hoped they are supposed to be there. So we'll fix that on the activities here. So we're going to jump into our activities and try to build up upon some of that information there. So let's start with this picture here. We got a bunch of points along the way in this picture, points A, B, C, and D, very creative points, and they're just scattered about the page. In geometry, you talk about planes, and in elementary school and high school geometry, you talk about Euclidean geometry, which there was a dude named Euclid that came up with all this geometry stuff and wrote it into this book. He has a book called Euclid's Elements, and if you ever want to read that book, it has got everything geometry in it. And what he does is takes you from page 1, starts talking about points, and he builds everything from that spot forward. And it's the way geometry was developed is basically, and it has proofs and gets into all of the different things that geometry requires to work. And then at the end of the book, he starts talking about things that if this didn't exist, if the Pythagorean theorem wasn't true, then this is also what happens. And, it gets into some what ifs out of that. But it's a great, great study. It's the geometry that we study, and just a good book about all of the things geometry. If I could ever understand the whole thing, I think I'd love to teach some upper division stuff. But I'm not sure that I can get there with it. But it's a great book. So Euclid's Elements, if you want to look at that at some point. So when we're looking at these points, they're happening on a plane. Euclidean geometry is flat surface geometry. When we talk about all the things that happen on a flat surface, we're talking about Euclidean geometry. And so all of these points we're considering them to be on the same plane. And we'll get into some three-dimensional things where more planes happen in the picture in just a little while. But the first thing says draw, and that is supposed to be a line, and it didn't quite come out with the arrows on the ends of it they're there, but they're not big enough. So there's supposed to be arrows on the ends of that. That's supposed to be line BD out of that. So we're going to draw line BD. So you need a straight edge and draw a straight line. So I'm going to use this thing to get there. Set it to 180 and hope it works. So I'm going to draw it in blue. That's what it asks for. And there's my line. Got a little tick in the middle there where the circles are. But we get a line, and anytime we draw a line, like it says, we're going to put arrows on each end of it. Important part of the notation that we get there. And then it asks us to place point T on line BD. Again, that's supposed to be a line BD between points B and C. So point C doesn't have to be on this line, but between B and C would be in this part of this line. So anywhere on that spot, put a point and call it point T. And so I'm just going to use a different color just to make it contrast real well for you there. And point T. And just anywhere, as long as it's to the left of where C is, you're good. But it's on that line. And then part C says give 3 other names for line BD. So 3 other names. So we're going to rename that line using the other points. So it doesn't matter what order the points are in, or as long as there are points on that line. So I could name this line point, or line BT would be one way to name it, just using the B and the T. Or what's another name? Can't use 3, only use 2. TD. And okay. No. No, not if we put the notation above it with the arrows on each end. We're not measuring how far it is between them. We're just naming the line based on the points that are on it. If it asks for array or a segment, you could, but it asks us to rename that line, so we need to call it a line because we're not changing what the object is. We're just changing the name of it. Exactly. Order doesn't matter. So yeah, DB would be a great one. Just go in the other direction. It's still the same line. All 3 of those names indicate the same object. They're just naming it differently, using other points or a different direction, starting in a different spot. Okay, so because it's a line, we can change the order of the letters, or we can change it. As long as we have 2 letters that are on there. You remember the old saying that the shortest distance between 2 points is a what? Straight line, right? So that's how you name a line, is using 2 points on that line. Any 2 points on that line. Doesn't matter if they're really, really close together, or one's at this side and one's at that side. Because technically, because that line has arrows on each end, what does it do? Keeps going on forever and ever and ever. So relatively speaking, B and D are probably pretty close together. Because if it keeps going forever toward infinity this way and infinity that way, those 2 points are pretty close together compared to other points that are on there. So if it asks for you to rename a line, then what you're renaming is going to be the same kind of object. Yes, there are rays that we could name from that, but it asks us to just rename that line. Part D asks us, that's supposed to be ray AC. So with rays, you put an arrow on one end, and you always start with your termination point or the starting point. It asks us to draw ray AC. So we're going to go up here to our picture, and from A to C, I'm going to draw a line. And it's not going to have arrows on each end. It's only going to have arrows on one end. All right. I'm just going to use a different color. So and again, the arrow goes on the end that's not the termination point. The name of a ray always starts with its termination point. Okay, so ray AC, and it asks us to do that in red, and I did it in purple. You change that to whale flitter. There's leak drawing in red. I want to break out the bottle of water. My voice is about gone for the day. So there's ray AC. Part E says explain why ray CA. So that's supposed to be ray CA. Is not another name for ray AC. Right. Starting point, the starting point is different, which indicates or names, whichever way you want to say that, a different ray. So if we have a different starting point, it's a different ray. Unless there's another point within the same, that's in between A and C or something like that. The starting point is different, then it's a different ray. Okay. If the starting point is the same, then they're going to be there. So look at F. So that's a good explanation on E. F says draw ray DA. That's supposed to be a ray. I don't know if you can see it on yours. I zoomed in on mine, and you can see the little arrow there, but it's just not big enough. I'm going to go back and redo these with a better arrow on there. Draw ray DA in orange and ray AD in green. So I'm going to go up here to my picture, and in orange, I'm going to draw ray DA. Longer straight edge here. Didn't bring my ruler today for no apparent reason. I guess I can go in there and get one. So ray DA starts at D and goes through A with an arrow on that end. And then in green, we're going to draw ray AD. And I'm going to try to purposefully not stack it perfectly on top of it. Yeah, I didn't do a very good job. You can still see a little bit of the orange poking its little head out of above there. So we see them going on there. So drawing those pictures there in the colors that they indicated. And then G part says, what's another name for ray DA? And they got underlined there for some reason. That's supposed to be ray DA union with ray AD. What's a union? This goes back to our 191 stuff with sets. What's a union do? So everything that's in both of them. Okay, so looking at our picture here, the union of ray AD and ray DA looks like what? A line. How do we name that line? Yeah, line AD would be a good AD with a line above it, or you could write the words line AD. That's also an acceptable way of naming a line. I like the notation with the little arrow above it, just because that's the shorter hand geometry notation. But line AD is also another name for that. What would be a different name for that? Line DA would also work. And then part H asks us to take ray DA and ray AD and get the intersection of those two rays. What's an intersection? The intersection is, it's in both of them, right? So where is that picture in ray AD and also ray DA? It's in between there, and you called it a what, Chris? A segment. So the segment from A to D. So segment AD or segment DA, it doesn't matter there. And when you Name a segment. It's just a straight bar over the top. You don't have to put dots on the end. I think in some geometry textbooks I've seen, they do put dots on the end, but the majority of them do not. So just a little straight line above it names that segment AD, or you could write the word segment AD. Those would be both. Or you could flip the letters around. Again, order doesn't matter on lines or line segments. Order only matters on rays. And that gets us to part I when we mention rays. It says, list two other names for angle ACD. So we've got to create angle ACD in our picture. So we're going to go back to our picture up here. And we've got ray AC there. And then ray AD that create that angle. So when we're naming angles, the vertex is got to be the letter in the middle. You could name it with three letters. Notice in our thing ACD, ACD would require us, excuse me, to draw a ray between C and D. We need to draw that ray. It doesn't matter what color. I'm just going to use a black line. What that does is it's going to create our angle ACD. I've highlighted that in black there, that's the angle that they're referring to. I had to add a ray to the picture from C to D, and then we already had a line segment from C to A, but I went ahead and drew the ray from C to A because an angle is supposed to be rays that are connected at one point. So this ray is connected at C. That vertex, the corner, has to be in the middle if you're going to use three letters. So the name that they used was ACD. Well, go the other direction, DCA. And the other name that it could be is it's got to be a certain situation for you to be able to name it angle C. The reason we can name this angle C is because there's no other angles coming out of that vertex. There's no other, there's not multiple things. Like if you had a picture that had that going on and C was right there, you had A, B, and D, then that picture, you could not name any of those angles by just the vertex because there's more than one angle at that vertex. In our picture up here, there's only one angle coming out of with C as the corner of it. So that's what allows us to do that. You've got to be careful about that. Only certain situations can you name an angle by one letter, and that's only when that's the only angle coming out of that.
So it would have been a line between C and D.
Yeah, if there were another point, like point F up here or something, I didn't put that in a good line. Put that in line there. Let me grab a straight edge so that it looks right. If there had been a point over here with F and you had another ray coming out of there into point F, then you couldn't name it point C or angle C because there's another angle that exists there. So the only time you can name by one letter, and that letter has to be the vertex, is when that's the only angle that shows up there. And we don't have any other points coming out of there. So I always like naming my angles by three letters anyway, because that's easy to follow when you go to your picture, and really helps you look at a diagram better. Okay. All right. So refresher on lines, segments, rays, angles, all that fun stuff there with number one. Now let's get into a three-dimensional picture, which introduces the idea of planes and sides. So planes are like the faces of an object, and we'll get into three-dimensional objects. We'll do a whole thing with those later on. Not today, but we got this square pyramid, I guess is the best way to decide this, because it's got a square as a base. And the description, it says, it's a two-dimensional picture of a three-dimensional pyramid with a square base. Note the base does not look like a square because we're kind of looking at it at an angle in this picture, but don't let that bother you. Sometimes it can kind of bother us a little bit. Three-dimensional drawings are difficult to do in 2D. Some of you may be very artistic and can draw or paint and do things in 3 dimensions very well. I've learned to do that a little bit for teaching purposes and art purposes, but it's strange that we live in a 3D world, but we really struggle at drawing a 3D world. So it takes some practice and some talent. So we look at this picture, we see the solid lines are supposed to be the ones that are closest to you. The dotted lines are the ones that are kind of in the back. So like if you look through this bottle of water, we know there are 2 sides to it, but if we're drawing it, it's very difficult to make that appear. So that's how we make it appear in a 2-dimensional drawing in geometry. Part A says list all the points that are shown and labeled in the drawing. So that's pretty easy, right? What are those points? T, U, and V, and my brain wants to go in alphabetical order, but it really doesn't matter. T, U, V, and then W, and then X. But it doesn't matter what order you list those in. Those points are what's in this picture. What are they called? No. Points can't be segments. Points make segments. But what are those points in the picture? Vertices or the vertex. When you look at this from T to U and U to V, that point right there makes the vertex of that angle that's happening there. So they're the vertices, which is the plural for vertex of the sides of this square pyramid that we're dealing with here. Part B says list all the line segments, even the ones that are shown with dotted lines in the drawing. You only have to name each segment once. Okay, so exhaustive list, one of our problem-solving strategies here. So I'm going to start with the bottom of the pyramid and get all those segments. So how many segments make up the bottom of the pyramid, the part that's sitting on the floor? 4 of them. So I'm going to start at T and go T to U segment, and then T also goes to where? W. So that's the 2 that come out of T. And then I'm going to go to U. I've already got T to U. So the next one to be U to V. And then there are no others that come out of U that are on the bottom. So I'm going to go to V. And V goes to W. And then do I need to list W goes to T? No, I've already done that with TW, right? So I've just done the bottom part. Let's do the rest of them. So what else? What other segment comes out of T? TX, the Texas segment. And then what comes out of U? UX. And out of V, VX. And out of W, WX. Why is he? All right. So we get all of our segments there. Count them up. There's 4, 5, 6, 7, 8. Count them in your picture. 1, 2, 3, 4, 5, 6, 7, 8. 8 segments that are listed there. So just make sure you don't list one twice out of that. All right. C part says list 3 different angles in the drawing that have T as the vertex. So that means T is where in the angle? It's in the middle of it. So when we name those angles, T should be the letter that's in the middle. Okay. So looking at her picture, I'm going to try to trace them as you guys tell me what they are. I heard XTU from multiple people there. So XTU is that angle right there. Right? So that's one of them. Good. All right. Let me write that one, XTU down. And then you said WTU. Is that what you said? Yeah, that's that angle right there. Good. T, U, and then X, T, W gets that one right there. Good job. Angle X, T, W. So there's three angles that have T as the vertex. Because there's more than one angle that has T as a vertex, can we talk about angle T in this picture? Definitely not. There's a lot of angles coming out of those spots there. All right. And then D, that's supposed to have arrows on each end. You can kind of almost see them there. They weren't as big as I was hoping. Okay, and then so it says draw line WT in that picture in red. So I'm gonna go up here to my picture, and we got to draw in 3D here. So when I extend line WT, when it comes out the front, it's gonna be a solid line, and out the back, it's gonna be a dashed line out of that. And I just took a straight edge, right, laid it right on those points, and extended it along there. All right, not a hard thing. And then we get into a little geometry term there with E part. It says name a line that is skew to line WT. And skew lines. What are skew lines? Does anybody remember that from geometry class from years and years ago? It's not on your sheet there. No, those would be intersecting lines. Okay. Okay, so lines that don't ever touch, but they're not what? Not parallel. What's it mean to be parallel? Your lines are parallel that go the same direction and never touch. Intersecting lines don't go the same direction and they run into each other. Skew lines are those special lines that don't go the same direction. They're not parallel, but they never intersect. So what that implies is they're not on the same plane. All right. So examples of lines that are skew to line WT. So what lines are parallel to WT? Or what line is parallel? There's only one. UV is parallel to it, right? And then TU runs into it, so we know it's not that one. And then WV runs into it, so we can't be that one. They intersect. So there are two possibilities here that we could use. What would they be? X and V and X and U. Those would be two that are skew. So either of those, it just asks for one, but either of those would do. So we could call it line XU if we extended it, or I said XV. And again, you could change the order of those letters and it'd be perfectly correct. Nothing's wrong with that. And then F there. Name three different line segments in the drawing that intersect line WT. VW. That definitely is one of them. Say it again. XW does. That's a good one. And then there are two more that could work. XT works. And that would satisfy the problem. But there is one more. Yeah, TU or UT, whichever one you want to. I'm going to put UT because where do we go to school? It asked for three. We named four because we're overachievers. All right. Okay. Not too bad. Now, G part gets it a little funky because it starts talking about Where did my G part go here? Flitter seconds. Yeah, we'll do it. I just didn't get it for whatever reason. It's not. I thought I copied it. It's a blank page there. It's like I copied it, but it's not there. Okay. G part says suppose alpha. So it uses the Greek letter alpha to name the plane that is square base of the pyramid, and beta is the plane that contains the triangle with vertices X, U, and V. So when we look at our picture, whoops, too far. Picture. There we go. This down here, the flat plane is alpha, and then the beta is XUV. So beta is like this side over here. Okay, it's that side that's leaning up right here. So we've got alpha is the bottom, and then the side that's leaning up here is the beta plane. Name the intersection of that plane, those two planes. And how do we know that? Is it points, U and V, or? Yeah, it'd be that segment UV is where those two sides meet, right? When planes intersect, they intersect at lines, right? It's the best example that I can give you in like everywhere you go of planes intersecting would be like these walls. This wall down this side is a plane. That wall back there is a plane. Where do those two walls meet? That corner there, right? That corner is a seam. It's a line. So when planes meet, it's line. They intersect at lines. Ours, because it's a limited figure, are going to intersect at UV or VU, whichever way you want to name that. Would be fine. And I would even, if you wanted to extend it to line UV, that would be 100% correct as well, because technically planes extend forever. The way that we're looking at this picture, we're looking at a limited plane because it's an object. But in theory, planes can extend forever. So their intersection would be a line that extends forever. But for us in this geosolid that we're looking at, it's a segment, but I would take a line out of that. They're both the same idea with that. Okay, so some interesting stuff there with lines, angles, segments, all of those fun things in geometry with that. So let's look at activity 7 now. And we're going to refer back to our definition sheet here and talk about, if you'll flip it over on the back side, and we're looking at this portion about the lines with the parallel lines in the pictures there. Let's talk about all the different types of angles that are created when lines intersect, especially parallel lines. So we have corresponding angles, alternate exterior angles, and then corresponding interior angles. So all of these things exist when we're talking about parallel lines and angle relationships. And my wife and I she's a little bit ahead of me in geometry. She's teaching geometry this time too. And she did a little activity with her kids, and I thought this would be really great to help learn that relationship. She was doing a little bit higher level stuff with her kids on it, but she took some painter's tape and just taped off part of the floor in the hallway outside of her room and made two parallel lines and then cut it with a line in between and had the kids race to get in the spot of whatever type of angle she was talking about in the and it helped them learn those relationships. So when we look at those pictures, so I'm gonna flip over here to that page. When we look at those pictures there, right there, the alternate exterior, this one has some color in it. I didn't get color copies for you guys, but corresponding angles is usually where we start. So let's go ahead and just do those first because there's more of them. Angles M and P are M and Q are corresponding angles. They're on the same side, and look at them, they're congruent to one another, they're equal to each other out of that. M and Q make a corresponding angle pair. O and S make a corresponding angle pair. N and R make a corresponding angle pair. and then P and T make a corresponding angle pair. Those are traditional corresponding angles out of that. So those pairs are on the same side with an angle between them. That's the way that I've always described them as the learning corresponding angles. And then you have corresponding interior angles. Okay, corresponding interior angles in our picture here. You've got the same picture as the above there. You already know that M and Q are corresponding. Well, O and Q are both on the inside together. They're what's called corresponding interior angles. You may have learned this in high school. It's called consecutive interior angles. That may ring a bell. I don't know if it does or not, but both mean the same thing. So consecutive interior or corresponding interior mean the same thing. So they're on the same side. They're both in between the parallel lines. They're on the same side of the transversal. This line that cuts through the parallel is called the transversal. Okay, same thing on the other side. We get P and R are corresponding interior angles out of that. Now, you also have what's called alternate exterior angles, or opposite exterior angles is another name for that. Alternate interior or alternate exterior all exist. If they use the word opposite, it means the same thing. Alternate and opposite mean the same thing. It just means sides of the line. You alternate sides of the line, it means you're on the other side. If you're on the opposite side of the fence, you're on the other side, right? So M and T are alternate. They're on opposite sides, and they're on the exterior, so they're on the outside of the parallel lines. So that's alternate exterior. S and N are also on the outside of the parallel lines, and they're on the opposite side of the line, so they're alternate exterior. Alternate interior, which is not on the page, but O and R are alternate interior. Because they're on opposite sides of the line, but they're in between the parallel lines. You might want to note that. Alternate interiors occur in between the lines and on opposite sides of the transversal. And on P and Q there, they're alternate interiors as well, because they're on the inside of the parallel lines, and they're opposite sides of the transversal. O and R are alternate interiors. P and Q are alternate interiors. Alternate exteriors just means you're outside of the parallel lines and you're on opposite sides of the transversal. Okay. What makes our activity a little bit more difficult is that they've paired it up with two sets of parallel lines and which created two transversals. So we got a lot of stuff going on there. So let's look at our activity and see if we can kind of decode it a little bit. It says in the figure below, answer the following questions. Line OR is parallel to line VS, and line UN is parallel to line TM. Okay, so lines are parallel to one another, each pair. In the picture, it looks like they are. But what that creates is, if you talk about these two lines as being the parallel lines, you've got cover up this line, and you've got all those different types of angles just for that line. And then cover up this line, and you got all of those different types of angles for this transversal. And then when you talk about these two being the parallel lines, cover up one of these, and now you got all those kinds of angles there. And then cover up this line, you got all those kinds of angles there, because there's a lot going on with that. So we've got to take it a piece at a time. So that's the easiest way to eat an elephant, one bite at a time. So easiest way to decode parallel lines and transversals is one at a time, one set at a time, okay? So part A asks us to list all the angles that are corresponding angles to MLR, okay? We talked about different types of corresponding angles. We talked about regular corresponding angles and corresponding interior angles. So we want to list them kind of separately there. So A part, first thing we got to do is, where is angle MLR? Yeah, it's right here. That's our home base. That's the angle we're talking about, okay? So if the two lines that are parallel that we're talking about are these two, and that's the transversal. Corresponding to that, regular corresponding is going to be same side, one angle between. Well, here's an angle between, so it would be this angle, right? So NIL is corresponding to MLR. So there's one of them, angle NIL, angle NIL. If we take the stance that these two are the parallel lines, and this is the transversal, where's the corresponding angle on this set? KLR is not corresponding. LKS would be, because it's same side, an angle between them. Okay, LKS would be how I would name that one. Angle LKS. There's two so far. Now, there's the regular ones. Let's get the, do we have, is that an interior angle? To be corresponding interior, where you got to be? In between the parallel lines, right? Is angle MLR, is it on the in between of any set of parallel lines? No, so we're not going to have any corresponding interiors, right? Do we have any other angles that would correspond to that angle in our picture? Let's see if we got them all. NIO is not corresponding. IJK, okay. Any others? Well, maybe we don't need a comma. I don't know. I'm waiting on you. Right. It's a different transversal, yeah. Okay. That would technically be a vertical angle instead of corresponding. Actually, I think IJK would be thrown out for the same reason as VJU is, that Katie was saying there, that it's a different transversal, so it can't be. So you couldn't use it as a corresponding one, because you can only have one transversal at a time that you're talking about. So only NIL and LKS would be the only corresponding ones to this one. Do what now? Two different, but they don't. So, and when your little darlings are doing the work even in elementary school, the picture that they put on that screen for them to do that Ames web testing and the case assessments that they're doing these days, that's the picture they're using. It's fun stuff where yes, it would be much easier if it was two separate pictures, but that's what you got to visualize. And you got a hand, cover up one of the lines, and you'll just get the letters that you need there.
The reason why angle IJK will not work is because line OR is the transverse line.
Yes, you're on the exactly right track there. Yeah. OR is our transverse there because that's where MLR lives.
So you can only work with a set of parallel lines and one transverse
at a time. Yes, that's correct. That's absolutely the perfect idea. All right. Let's move on to B. List all the angles that are opposite exterior. Opposite exterior is also, remember that also you could call that alternate exterior. So if you Google this and you look up opposite exterior and it comes back with some stuff that says alternate exterior, it's the same thing. Okay, opposite exterior. So VJU. All right, VJU. All right, so I'm going to get rid of my highlighting there. I'm going to highlight VJU. So let's pick a pair of parallel lines first. Which pair do you want to talk about as being the parallel ones that we're gonna focus on them first? Okay, so these two, that's the ones that are their parallel lines. So what's that mean about this other line? This line here doesn't exist at this moment. So we're pretending that that's not there. Does that help?
Yes.
Okay. So we're pretending that that line doesn't exist at the moment. So we want alternate exterior. We're going to need to uncover that because we need one of those letters that's there. But that's the idea, is that we pretend that this line does not exist. Very good. LKS. Because what we're treating is if we say that line doesn't exist and we're talking about these two being our parallel lines, then the only transversal that I have is this one. That's the transversal. And you can only deal with one transversal for a pair of parallel lines when you're talking about angles and things like that. Okay. So that alternate or opposite exterior means it's outside of the parallel lines. So the parallel lines are here. These are the two that we picked to start with. If these are the parallel lines, then outside of it, it's got to be these angles. The only exterior angles are these four, because this is our transversal. So okay. Opposite means flip the side of the line. So on the opposite side of the line, this one's not outside exterior to this angle. There's an L right here, or you can name it MKS if you want to. That's the same angle. No, it's on this line, isn't it? So technically, it doesn't go away, even though it's on the other line too. It's still on this line, so you can name it MKS or LKS.
Oh, would IJK?
Where's that at? I's up here. IJK. No, it would, because where's it at with the parallel lines? It's inside of them. It's not exterior. TKS is not alternate or opposite because it's got to be on the other side of the line. So if we're on this side, alternate or opposite means you got to jump sides of the line and go to the outside. So this is here. And y'all, I wish I had some painter's tape now. We play that game where you got to go to that place. So it's got to be either LKS or MKS. It doesn't matter. It's okay if you name it MKS if you want to. Okay, is it starting to make a little bit more sense? It's probably been a while since you guys done this, and I understand that. And what's weird is that who all had to take geometry in high school? Everybody? Okay, you took a geometry course. It's 10th grade now. 10th or 11th grade now. Yeah. So 10th or 11th grade takes geometry. Most of the time, 10th graders at this point, the way the state likes for you to do it, it technically doesn't matter. But you take one semester of geometry and usually 3 semesters of algebra stuff, right? Did you?
I had algebra 1 my freshman year, sophomore year,
Did you have for geometry? You didn't have it all year. I don't think so. A different class? Yeah, we're on blocks, 4x4 blocks. So algebra 1 is the only year-long math class that we have. I don't know. All right, I'm gonna name that LKS just so Maggie's not right. All right, so either way, you take one semester of geometry, so 1/4 of your high school math curriculum that you're required to take is geometry, 3/4 of it's algebra. So not remembering this stuff, I understand. What's weird is the ACT test is 40% geometry. Yeah.
The practice, the math, is geometry.
Yeah, it's a lot of, yeah. Is it the middle school one or the elementary math part? All that stuff is part of the curriculum now. They try to mix it in. There's a high school curriculum that McNairy County doesn't go by it, but there are several of the larger systems in the state that do this. It's called integrated math, where you don't take a separate geometry class. It's integrated math 1, integrated math 2, integrated math 3, and they mix in the geometry standards with the algebra standards, and it works about the same as what we do, but it's just you don't have a purely geometry class. So maybe it's a little bit easier on you if you're not good at spatial sense and all that stuff. All right. So there's one of our angles. Now, again, we're talking about angle VJU. And we covered up this line over here first. Well, what if these two are our parallel lines and we pull the old disappearing trick with this line? That angle doesn't exist anymore because we took that line out. NIR or NIL, whichever way you want to name that. Yes. This angle right here would be alternate exterior to that. Or opposite exterior, same thing. NIL is how I'm naming it. All right. Not liking it as much as you were. Yeah. Okay, Chris. No, because that line doesn't exist anymore. Because in the second, because we can only have one transversal in a set of parallel lines and have those angle relationships exist out of that. Technically, we would be able to prove that MLR and VJU have the same measurement, but relationship wise, they are not considered alternate exterior or opposite exterior because they're not on the same transversal. That's the reason. That helps. A lot of times that helps. Just rotate your paper and cover up the part you need. Get you a little slip of index card to cover up the line you don't want out of that. All right, let's go to the next thing. List all the angles that are opposite interior or alternate interior to IJK. So IJK, highlight that angle. IJK. So we've got to pick the set of parallel lines we're dealing with. Okay, so that means that we're covering up this line then, right? If the two parallel lines we're dealing with are these two. Alternate interior means the opposite side of the line, but in between the parallel lines. ILK doesn't exist. This line doesn't exist down here. Opposite side interior, so that means it's got to be inside here. IJV is not, it's on the opposite side, but it's not, it's considered a linear pair with that, not an alternate. OIJ, that's the right one. Keep guessing, you'll get it right. So that's if these two were your parallel lines. Let's take the other scenario that these guys are your parallel lines. That means that this line no longer exists. No. So JKT, that one right there. JKT. Again, you've got to cover up the line that you're not using. Alternate or opposite interior means you're in between the parallel lines and you're on the opposite side, but you can't be touching it. Okay? You're not adjacent is the geometric word for that. Adjacent means touching or right beside. So you've got to flip sides and go away from it.
But you can still use the point.
Yeah, you can still use the point because you're just going to have to name it by the. Yeah, you can use the points, but you can't use the corners. Can't touch. Alternate or opposite interiors or alternate interiors. The vertex can't be the same, or it's not one of those things. Okay. All right. We may not get through this.
I remember doing this in high school, which makes me want to actually work, but it helped me where I couldn't see both of them, like one out, I just quickly sketch.
Just draw yourself a different picture, a separate picture. Yeah, that would probably help you. If you're struggling with covering one up, draw yourself a whole other picture, or get you some what we use, patty paper. You can go and it's like the paper, they call it patty paper because you put it between hamburger patties if you make a bunch of them, and it's clear, you can see through it and you can write on it, and you can just trace the picture and only trace the parts you need, and then look at that picture separate. It's one way of doing that. So that's a great idea, Casey. Thank you for sharing. That's awesome. All right. D part, 3 angles that are supplementary to RK or RLK. So RLK is right here. Supplementary, what does supplementary mean? Angles equal 180, and that's on your reference sheet there. If you'll glance back to the front side of that, supplementary angles right there, they add up to be 180. So let's kind of try to build that here. So easily adding to be 180 means you make a straight line, so because a straight line has 180 degrees in it. So what angles create a straight line with this one that we have highlighted? So straight angles. MLR would be one, because from added with, yeah, that's already there. It really has nothing to do with the parallels too much at this point. So angle MLR is the one you guys said. ILK, which is this one here, makes a straight angle with that. So that's easily 180 degrees. ILK. OIJ. Why can you do that one? That's correct. What's the reason? So that we can explain. And what do we know about angle ILK and OIJ? They are what kind of angles? Nope. What do we know about this angle and the other angle that's in red there? What kind of angles are they? Corresponding. Corresponding angles are equal to one another. So that's why they would still be supplementary. So that would be the explanation. If you had to explain why is OIJ and ILK both supplementary, well, they're corresponding, so they have to be the same. So what's also corresponding to MLR? MLR and VJQ, they are not corresponding, but they are, okay. NIL would be the corresponding one to that. So both of those will work. down the right one. Angle NIL, because that's corresponding. And then the angle VJU also works. See if we could find another. If there is another. JKT, because it is corresponding to ILK, right? So that's good. JKT also works. Lots of them. How about that one? It asked for 3. We definitely have overachieved here by using our corresponding angles to help us get there. It just asked for 3. So we put a limit on how many because they're a lot out of there. So just ask for 3. So pick 3 there to get you there. All right, easy enough. This sounds, that's bad. Easy enough. It really wasn't that easy. Okay, here's where the protractors come in. Okay, so protractor. So if you got this kind, this is what I'm going to use. But if you've got this kind, I'll show you how to use it too. I'm going to show you on the screen out of that. So with the protractors, if you got the little semicircle style, then it should have a hole right there in the middle at the bottom, and there should be a line extending out of that hole, or mine does. If Katie, yours is a little bit different. It does have a hole in it at the bottom right there. Okay, so the hole goes on the vertex of your angle. Okay, so when I'm measuring this angle, I'm going to put that right there on that little dot that's A. Okay, and then I'm going to line up the line that goes into that hole. I'm going to line up with this ray AN. Okay, the screen's moving, so it's messing me up here, but line that up as be very picky, okay? And then I'm going to look at where that other ray goes through the protractor up here where it's got the degrees marked. I'm getting somewhere around 73 or so, 74, something like that. That measurement there is probably not the best place. If it isn't long enough, you may have to extend it, extend the ray to get up there. I'm getting 73 or so, 73. If you're using this type of angle measuring device, protractor, same idea. It's got the hole there in the corner that goes in the corner, and you line up the lines that are in the center with your rays. So they're in the corner, line up, and then turn this to where the ray is there. And then this one, it doesn't have enough calibration there really to get very accurate, but I can see that it's between 75 and the 70 mark. So I could get a good estimate there. So this works. It's probably not, it's got a little bit of a, if you'll notice right here, there's the more calibrated part, and that it's plus or minus 5 on either side. So when you go to that and I measure that, I'm gonna measure it on my screen here because it's the lines are too thick there to really get a precise measurement. Line it up here. Get it. All right, so the 70 mark, and then it's about 3 of those tick marks to the left of the 0 in that little spot. It was, yeah, because I'm only getting a little bit here. We gotta make it just so it's kind of in between 72 and 73 by all accounts. But if you put 72 there, that would be fine. I'm gonna put 73 because that's what I think it is. So 73 degrees. Is that acute, right, or obtuse? And it says explain. Okay. Angle PAM is acute because its measure is less than 90 degrees. We know right angles measure what? Obtuse angles measure greater than 90. So knowing those definitions, important part of geometry. Basically, consider general knowledge at this point, I think, for us anyway. All right. C part says list three more names for angle PAM. So DAN, PAN, okay, or DAKM, or can I name this one with one letter? Yeah, because there's no other angles coming out of there, so I could name it just angle A. It asked for 3, we did 4 because we're overachievers. But again, that rule about how many, if there's more than one angle coming out of a vertex, you can't use one letter. But if that's the only angle out of that vertex, one letter is the easy way. Okay. D part says, what would a measure of an angle that is supplementary to angle PAM be? So if it's 73, so we take 180. The explanation would be show me the math that made it happen. 180 minus 73 equals 107 degrees. And maybe just put their supplementary angles. Add to be 180 degrees. Okay. Oh, number 3's got another picture. Woo-hoo! I'm excited about that. That's a lot of pictures. A lot of letters in there. It's kind of bunched up close together. It makes it fun. In the diagram, line OR is parallel to BS and UI is parallel to MK. And let's suppose that the measure of angle VQU, this angle right here, is 55 degrees. Fill in the blanks below. The first blank for each part should be filled in with one of these: supplementary, complementary, corresponding, opposite interior, opposite exterior. So supplementary, complementary, corresponding, opposite interior, opposite exterior. 5 choices for the first blank, and the second blank will be the measure of the appropriate angle. Okay, so QWK and VQU, just the one we know about, are what kind of angles? So let's look at where is QWK? Is right there. What kind of angles are those two? Corresponding. They're on the same line that cuts through 2 parallel lines, and they're on the same side, but they're not in between the parallel lines. So that's corresponding. Corresponding. And so if they're corresponding, we know that they are what? The same. So this would be 55 degrees. The next question asks about angle KWS, and then the one we know about. So I'm going to go up here, KWS. Uh-oh. Supplementary. Good job. That's right. Can you tell us why? True. But how do you know that that angle there is 35 degrees or 125 degrees? How do you know that? It's corresponding to UQW, right? And UQW and VQU are linear pair or supplementary. So those two have to be supplementary. Yeah, supplementary is the right answer. I just want to just get that explanation for everybody else to be able to see that. So that would mean that it is 125 degrees. And again, that's 180 minus 55 equals 125. That's where that's coming from. Okay. No, you wouldn't have to there. I'm just showing that to where so we know where that number is coming from. So if we didn't just pull it out of the air or somewhere else. C, MZR and VQU. So MZR, I'm gonna go up here and MZR. Wow, way over there. Opposite exterior would be a good way to describe those. Opposite exterior. I'm having to break myself from calling them alternate exterior. The verbiage is opposite exterior now. They changed that for no good reason. So it's old guys with gray hair that get confused. So if they're opposite exterior, what do we know about them? They same degree, so that's 55. Ooh, D picks up a different pair. It says angle QWK and IPZ are what kind of angles, and then what do we know about there? And then so let's look at the picture first to get the fill in the blank part. So QWK, so QWK is here, and then IPZ is there. What would they be? Well, but they're on different transversals if you call them interiors. And the same reason you couldn't call them exterior either, because they're on different transversals. But you could call them corresponding because they should be the same, right? Kind of through the grapevine, you know that QWK is corresponding to VQU, and then that we also know that PZW is corresponding to QWK, and then we know that PZW and IPZ are the same because they are corresponding or opposite interiors. So that it's kind of a roundabout, but they're corresponding angles. And well, I'd say corresponding would be the right method there, and it should be 55 out of that. Okay. So this activity 7 is a tough one. I mean, the parallel lines, a lot of stuff going on there makes it a little tough to do. But it's doable. It's not outside of the realm of your abilities. So I think activity 8 and 9 are a little easier, in my opinion, than this. This one is the toughest one of the week. So let's go to activity 8, and let's talk about curves and polygons a little bit. So just a lot of real wide, broad strokes here with geometry, which is what a lot of the elementary geometry is, real wide, broad strokes. Don't really drill into the specifics of it as much, except for on parallel lines. That for some reason picked that one to really zoom in on, but everything else is real broad. So when we're talking about a picture here, it wants us to fill out this little chart that's underneath there that talks about simple curves, closed curves. I never can say this right. You can call it polygonal. That's accepted way, but I had a professor that called it polygonal curve. I don't know which way is really the proper way, but polygonal, it sounds easier to understand. So that's what we're going to call it. And then whether it's a polygon or not. So what we're going to do first is define all of those things, and then we'll look at filling out the chart. So a simple curve, what that means is it doesn't cross itself. Okay, so a simple curve never crosses itself. Okay, so looking at that picture, let's go ahead and fill in that line of the chart at all three of those pictures. Is A a simple curve? No. Is B a simple curve? Yeah, it's a curve, and it doesn't flip over itself. It doesn't twist up. Maybe it's the right way to say that. So yeah, that's a simple curve. And then C. Does it fall across itself? No. So that's a simple curve as well. So those two are simple curves. And now let's talk about a closed curve. A closed curve, its definition is it encloses an area. That's the best way for me to describe it to you. Encloses an area, and there are no endpoints. Maybe that's another key to that. Enclosing an area and no endpoints. So looking at our pictures here, which ones of those enclose an area? A and B. A happens to enclose two different areas, but it still meets the definition of enclosing an area. It closed it up, and so closed, shut the door, there's nothing's getting out. That's the idea. And then C leaves the gap, and these points right here would be considered endpoints because the lines stop. So that's that other half of that definition. So A and B would be closed curves here. So that's what a closed curve is. And a polygonal curve, it creates a polygon, and a polygon has no arcs, and it's made up of line segments. When I say arcs, I mean a curved line. Okay, so a polygonal curve has got to be a closed curve, and it also has to be segments, though. Okay, so a polygonal curve is a special closed curve. So A and B were both closed. Which one of those is polygonal? A, because its lines are all segments, right? B is an arc, so that's why it's not polygonal. So A is the only one. And well, is C polygonal? It's made up of segments, but does it enclose an area? No, so it's not closed, so that's why it's not polygonal. Yes, polygonal is a special closed curve. Okay, a polygonal curve has got to be closed. So if you're going to be a polygonal, you got to be closed. And then which ones of those make up a polygon? Well, A, because it has a polygonal curve, right? And then so closed figure. Figure has an arm. A convex. When you talk about convex, the definition of convex is all interior angles are less than 180 degrees. So interior angles there for A and C there are the only ones that have angles. The arc doesn't really have angles. The curved one doesn't. The A, all of those angles on the inside of that are less than 180 degrees. This one, if this were closed here, this wouldn't be a convex figure because this angle here measures more than 180. If this were closed, we're hypothetically speaking here. None of these, technically, A is a little bit suspect because of the crossover there, but we'll call it convex just because it's two convex figures in one picture out of that. But so we'll call it convex there because all of the angles on the inside of it, both of those figures are less than 180. The way I've always remembered it, convex doesn't cave in, concave does. Concave, if something caves in, so you got the sides of a figure. If it's concave, then one of the sides caves in, like falls in. That's the way I always remember it. Convex, it doesn't fall in, and that satisfies the idea of that. So those definitions are important. Knowing those things or what those are, so you can look at pictures and classify some things. Number two, we're thinking about a figure and talking about a property, and we're going to talk about those things. So I'm just going to go down here below this, and we're going to draw all those figures. What's a trapezoid look like? I don't know. Remember what a trapezoid looks like? This is what one of my son's favorite figures when he was little was a trapezoid, and like he was 3, and he would talk about trapezoids. And everybody's like, well, how does he even know what a trapezoid is? His parents are math teachers. That's how. But a trapezoid, it's also one of the tangram shapes, which he likes. So there's an example of a trapezoid. It's not the only kind of trapezoid you could have. You could have a trapezoid that looks something like this. That's also a trapezoid. We all know what a square looks like, right? We need to draw a square. I think we got that one. Parallelogram. Or as my favorite geometry teacher at our high school calls it, a parallelogram. She doesn't use the A there. She's saving them up for a trip. The parallelogram always reminds me of the state of Tennessee. Parallelograms. Octagon. That's where everybody fights, right? You fight an octagon. So 8 sides. We're used to the what's considered a regular octagon. Yeah, the stop sign. That's the one we're used to, but that doesn't necessarily mean that every octagon is regular. What's it mean to be regular in geometry? Much different than in everyday life if you're regular. It's a bad joke. Sorry. It's a dab joke. Regular means all the sides are the same length. But octagon, you just got 8 sides. That's all it means. It doesn't necessarily mean that all sides have to be the same. But if you say regular octagon, you're talking about a stop sign. It's a regular octagon. Isosceles triangle. Isosceles. What's an isosceles triangle? You guys remember? That's equal angular or equilateral. All the angles would have to be less than 180, but isosceles is where the 2 sides are the same. Equilateral is where all 3 sides are the same, and as a result of that, all 3 angles are the same. So equilaterals are equilateral and equal angular. Isosceles triangles, 2 sides, at least 2 sides are the same. Isosceles triangle. If you ever remember the show Seinfeld, Kramer wanted to name his kid Isosceles Kramer. I tried that. It got vetoed, so they couldn't name their kid Isosceles Isbel. She said it had too many S's in it, and if he had trouble saying his S's, he'd have trouble in school. So I think that's the reason she told me. She vetoed it. I think it's because she just didn't like it. So I vetoed some other name. All right. So be careful when you read these statements. Always is a very big word. It's a word you never use in an argument with a loved one. Right? Mitchell ever uses the word always. You call me, okay? All right. And I will explain to you how he could not use that word. All right. Always has exactly 1 pair of parallel sides. So that means never not that way. Okay. So which of those shapes always, every single time you draw a trapezoid, Does it have two parallel sides? Yes. Okay. When you draw a square, does it always have exactly one pair of parallel sides? It has two pairs. That's not exactly one pair. Oh, so yeah, it gotcha. And then parallelogram. How many pairs of parallel sides do parallelograms have? Two pairs, not exactly one pair. So they can't put a check mark there. Octagon. Not necessarily. The stop sign we're used to seeing, yes, it's going to have, well, no, the stop sign will have more than two pair, have four pair of parallel sides. But that is not going to be the case with an octagon. Isosceles triangle. Do you ever have parallel sides with triangles? If you do, you're looking in a funny house mirror or something. That don't work. All right. Statement 2 always has exactly two pair of parallel sides. So which ones can we put a check in? Square and parallelogram. The rest of them are no-nos. Now, here's where they throw, put a little spin on the ball here. Could be concave. And remember, concave means it caves in on one side. And the interior angle is greater than 180 degrees. So can a trapezoid be concave? How so? Draw me one. Gotta have four sides to be trapezoid. A square couldn't be concave, right? Because a square always has 90-degree angles in the corners, right? Parallelogram, could it be concave? Because it's the state of Tennessee, right? Is there any way that you could bend that around and make it cave in? No. What about an octagon? Just got to have 8 sides, right? I could draw an octagon. 4, 5, 6, 7, 8. There's a concave octagon. It's got 8 sides. An isosceles triangle definitely cannot be concave. Must have 4 right angles. Square is the only one. Could have only 2 right angles. Trapezoid could have only 2 right angles. That word could is important. It doesn't say always. It just means can you draw one that does that? Can you draw a square that could only have 2 right angles? It's got to have 4 or none. There's no in between. What about a parallelogram? You make 2 of them right angles. What are the other 2 going to be? Right angles as well. It's going to make a rectangle out of it. So if we take this state and lean it up to where they're 90, that creates 4. So that can't have it. Can you draw an octagon with only 2 right angles? I think so. I could draw one that's concave. I figure I could just draw a couple of right angles and then do some funky stuff there with the other sides and make it work. So yeah. And then is there any way a triangle could have 2 right angles? Definitely not. All right, next one could have only 1 right angle. Can a trapezoid only have 1 right angle? If it's got to have exactly 1 pair of parallel sides, then it can't have just 1 right angle. Is there a way? We've already established the square's got 4, so no need worrying about that one. Parallelogram, one of them becomes 90, then the rest of them lean up to be 90, so that doesn't work. Can we draw an octagon with only 1? I think so. And can an isosceles triangle have 1 right angle? I draw this triangle and then somehow intersect that bottom side to where these 2 are the same. That's isosceles, and it has a right angle. So yeah, I think so. And then always has at least 2 sides that have the same length. at least. That's the big word in that one. Trapezoids, do they have sides that are the same length? Always? Not always. There are trapezoids that have two sides that are the same length. They're called isosceles trapezoids. So that means, where can I put a check mark? Isosceles triangle has to have two sides that are the same length. A square is going to have at least two sides of the same length. Happens to have four. That's an at least issue. What about a parallelogram? Yeah. Technically, a square is a special parallelogram, isn't it? So that works. Does an octagon always have two sides that are the same length? No, not always. The stop sign we're used to does, but not every time. Okay. Next page. That was a little easier. We got this big triangle. I copied the picture first, and it asks us to measure the angles using the protractor and label them in the picture. So measure those angles with your protractors in that triangle and let me know what you got. And I'm going to label by some letters here. So I'm just going to do A, B, and C. So when I ask you for angle A, y'all tell me what angle A measures and what angle B measures. And hopefully we get it right. What y'all get for angle B? The hole in the center of the corner. Line up with the edge. Or with the ray. Make a choice. So yeah, because you want the angle you're trying to measure. You want to put the circle right with the corner to be right in the center of that, and then put it there. You need to line up this line with that ray. They do the same thing around. 2, 44, and 74. That's what you got there. Put your circle on the corner. Now, line up this. Line this there. Line it up with one of these, with this edge here, so that because you're measuring this thing from here, you want to line that up. 73, 70. I think someone will get 73, 74. Yes. Yeah, if you want to borrow it for this week, just make sure you bring it.
Yeah, well, we haven't started today.
Okay. I don't know. You want to tell her that you're going to kill me for letting you borrow it. So, B, y'all got what? 40?
B got 62.
62, and then A was 44, 62, 44, and then C would then have to be what? 74. And then, so for B part, so somewhere around those measurements, you get close. But what do we know they should add up to be? They should add up to be 180. These happen to do that. I don't know if that was by design or by just foreknowledge. We did 44, 62, and 74. It's 180. And then, did you expect this to answer? Why, yes, indeed I did. I'm smart. I knew that happened. Is this triangle equilateral, right triangle, obtuse triangle, or acute triangle? And why? Explain. Explain to me why you call it an obtuse. That has nothing to do with being right. If it's a right triangle, it's got a 90-degree angle. Why is it an acute triangle case? All the angles are less than 90 degrees. They're all acute angles, right? We know the rule for acute angles is that they're all less than 90 degrees. So, excuse me. Y'all, I guess this means it's time to quit and go home, right? I'm sure y'all, I would love that too, but we're going to have to finish it. So all the angles are acute, so it's an acute triangle. How many angles have to be right for it to be a right triangle? How many can be right if it's a right triangle? One. Because remember, they got to add up to be 180, right? So how many angles are in every triangle? 3. So if one of them is 90 degrees, what do the other 2 have to be? Less than 90 are acute angles, right? So this is an acute triangle because all angles measure less than 90 degrees. So that would be your explanation. An obtuse triangle, how many obtuse angles can there be? 1, only 1. Okay. Equilateral triangle, what does that mean about all the angles? They're all the same. Equilateral technically means all sides are the same length, but as a result of that, all the angles have to be the same too. So equilateral, equal angular are both the same kind of thing. So know those differences there. That's a review of a little bit of triangle stuff. Number 4, we got to do some creative drawing here. I used to do this activity for a few years when I was teaching geometry. It was called Quick Draw, and I would put a picture up on the screen and leave it up there for 5 seconds, and then black the screen, and the kids had to draw it. And it was just to get their brains going on the spatial sense. And it kind of helped a little bit. And this is kind of the same idea, except for I don't give you the picture, I give you the description, and you draw a picture off of it. So the description is a non-convex. So remember, convex means it doesn't fall in on itself. Okay, non-convex would mean it does what? Falls in on itself. It's concave. Non-convex and concave mean the same things. Hexagon with one right angle. So hexagon means how many sides? 6. So we got to know our Greek prefixes here. So triangle, tri means 3. Then we got quadrilateral, which is 4 sides. Pentagon is 5 sides. Hexagon is 6 sides. 7 sides is a heptagon. 8 sides we know. 9 sides. Nonagon or non-gon is the way I always remembered it, but nonagon is the right word. And 10 sides, decagon. DEC is decagon for 10 sides. And then 11 sides we don't have a name for. There's not a prefix in the Greek language for 11. So we call it an 11gon. 12gon is, or a 12-sided figure, you can call a 12gon or a dodecagon is the same. I don't know. Something about why does no building have an elevator with floor 13? I don't know why they skipped 11. That's beyond me. I've looked and I don't know. I haven't done that much research on it. It didn't bother me that much. No building has a 413. But we don't call it 13th floor. Yeah. Bad luck. I don't know. It's just what they did. So let's draw a hexagon with one right angle that's concave. Okay. So I'm going to start off by drawing my right angle so that I ensure that that's happening. So I'm going to draw a side, and then I'm going to measure myself a 90-degree angle. I'm just going to make a little mark here so that I can draw that side to be 90 degrees. It doesn't matter how long it is, but I know that that's 90 degrees, and the indicator for that to be 90 is to put a little box in the corner that says, hey, there's my 90-degree angle. And now I'm just going to put, I've got two sides. I need 4 more. So it also said non-convex. So I'm going to make one of these. I'm going to make this cave in here. And then come back out. So 1, 2, 3, 4, 5, 6 sides. There's me a hexagon. Not the normal hexagon we're used to. We're used to seeing the nice, pretty, regular hexagon. That's the beautiful little picture. But here we're just trying to be creative and make that look weird. All right. B part says a concave pentagon with exactly 4 sides that have the same length. The 5th side must have a different length. So if you got your protractor, it's got a ruler on it somewhere. Pick yourself a length. And we're drawing a pentagon. So it just means we're used to the pentagon shape that we grew up with. That shape. That's what we're used to. But we're trying to draw a concave pentagon, so it falls in on itself out of that. So I'm gonna draw my sides that are the same. That's 1 inch on my ruler, and I'm gonna make sure it's concave by doing this. And so there are 4 sides that are all the same length. I measured them. They're exactly the same length. And my 5th side is right there. So that's 1, 2, 3, 4, 5 sides, and it is concave. It caves in. It's a pentagon with 4 sides that are the same length, a 5th side that is a different length, and it's concave. Concave means it falls in on itself. Convex, it does not fall in on itself. If it asks for a convex pentagon, then this interior angle right here, that's the one that makes it concave, because its interior angle is greater than 180. So concave, the angles are greater. At least one of the interior angles is greater than 180. Convex, none of them are greater than 180. So just got to be a little creative with your pictures. Make it fun. All right. Activity 9. Yay. We're getting there. We'll get to 10 and you can really have some fun. Activity 9, angles in polygons. So the first little problem here says, what's the name of a polygon shown in this picture before to the right? So what do we name that polygon? How many sides? 1, 2, 3, 4, 5, 6, 7. 7 sides. So it would be a heptagon. Or you could call it a 7-gon. This is the more accepted answer. There is the heptagon. But a 7-gon is the lazy man's way of naming that sucker. All right, now, it would technically be a convex heptagon. It's not concave. B part for this problem says, what's the sum of the measures of the interior angles in this polygon? Explain how you could find this sum using triangles. Use the point shown at one vertex and draw the triangles you would use to calculate the sum of the interior angles. What do we know? Why are we using triangles? What do we know about the angles in a triangle? They add up to be 180. So if I can fill this thing up with triangles, then I can just count how many triangles I have and multiply that times 180, and that'll give me all the measurement of the angles inside. So here's the point that they're referring to, that little point right there. So I'm going to draw triangles from that point. So I'm going to draw a line and create a triangle right here. There's one triangle right there in the top. So one. And then I'm going to, from that same point, connect to the next vertex. So there's the second triangle. And I'm going to connect to the next vertex. There's triangle number 3. And then there's another triangle right there. That's triangle number 4. And here is triangle number 5. So I drew 5 triangles inside of there. So 5 times 180 degrees is equal to 900 degrees. There is a formula that you learn in geometry class, and in elementary geometry it's taught as a formula as well, that the sum of the interior angles of a polygon is 180 degrees times n minus 2, where n is the number of sides. That's the formula that you need. Okay, so that works for squares. It works for 167 gons, dodecagons, all of that stuff. So that's the formula that we're using those triangles to meet, because we were able to draw 5 triangles. That we're 7-sided figure, right? 7 minus 2 is 5 times 180. That's the 900 degrees that are in there. If you took your little old protractor and went around and measured all those interior angles, nobody'd want to do that. That really, it's hard to do because the sides are short and all that stuff. But you could do that, and it would add up to be 900 degrees, or really close, depending on your estimates one way or another out of that, okay, for that 7-side, that heptagon there. So that little formula is what you need to be able to do the interior angles. Interior angles is sides minus 2 times 180. So when you get to part number 2 there, it says, what's the sum of the measures of the interior angles on a 28-sided polygon? 180 times 28 minus 2. 180 times 26. And everybody knows they're 26 times tables, right? Yeah. Yeah, 180 times 26. Did you know that? All right. 4,680 degrees on the inside of that. Explain without using or without measuring the angles. We're using the sum of interior angles. Okay. What's the sum of the measures of the exterior angles, one at each vertex of a 28-sided polygon? This is a trick question. No matter what size of a polygon you have, the exterior angles always, that's a big word, add to be 360 degrees, no matter what size. square exterior angles. And what we're talking about by exterior angles, if we had like a pentagon, and I'm just going to draw some sort of weird pentagon here. The exterior angles are these angles right here. Those outside angles, that's the exterior angles that it's talking to. Bless you. So the sum, no matter how many sides it's got, it's always 360. Always. That's a rule. If that rule is not in place, some of our Euclidean geometry starts falling apart out of that. Just it's always the case. So that is a rule. So that's kind of a trick question there. All right. Number 4. What measure is the measure of each interior angle of an 18-sided regular polygon? So again, regular means what about the sides? All the same length, right? That's what regular means. So same length on the sides. So we need to find out first how many degrees or how much, what's the sum of all those angles. So we're going to find the sum of the interior angles. So that'd be 180 times 18 minus 2, 180 times 16. 2880, right? 2,880 degrees. That's the total. How many interior angles do we have? That'd be 18 of them, right? 18 corners in there. How many times does 18 go into that? 160. So that means every one of those angles is 160 degrees. 160 degrees at each vertex. That's our final answer out of that. Okay. Your explanation is showing that you're using the sum of interior angles formula and then dividing by the number of vertices that you have, or corners that you have. You always have the same number of corners as you do sides. Always. Okay. 5. What's the measure of each exterior angle on an 18-sided regular polygon? What do we know about exterior angles? Always equals 360, the total. So we're going to take 360 divided by 18, which is 20 degrees at each vertex. And it's something, your explanation would be, we know, the sum of exterior angles is always 360 degrees. So you need to say that at some point there, so that you know where you're getting that 360 at. 6. What's the measure of each central angle on an 18-sided regular polygon? So central angle means, let's take a smaller figure. 18-sided is a little too big for me to draw. So let's draw a smaller one. Let's draw a square. And I'm going to change that to make it a good-looking square. That's a good-looking square. A central angle is you find the very center of that thing, and a central angle is those angles there, where you just go out to the corners. This is a central angle. So on an 18-sided, so here we know that the sum of the interior angles would be how much? Or think about the center of that thing. If we're going to add up all of these, what should it add up to be? with a square, it's going to add up to be 360. If it were a regular pentagon, what would it add up to be to go all the way around? It add up to be 360. The central angles and the exterior angles all add up to be the same thing. Because to go all the way around the shape, you're going all the way around the circle, right? So all the way around is 360. Right? So that's the reason for that. So for us, in an 18-sided figure, regular figure, you're going to be 360 degrees divided by 18 again, which is that 20 degrees. Central angles add to be 360 degrees, always. So those central angles are right in the center of that thing. Okay. All right. Number 7 is our dot paper. It says on the dot paper below, draw a lattice polygon with the sum of measures of the interior angles being 1260 degrees. And then we need to explain how we knew how many sides our polygon would have. And then it tells us what a lattice polygon is. A lattice polygon is simply a polygon whose vertices are on the dots in the grid below. So your polygon can be convex or non-convex. It doesn't matter. You get to choose there. So first off, we need to decide how many sides does this thing have. So how can we figure that out? Okay, so the formula is 180 times n minus 2 gets you the sum of the interior angles. But we know the sum of the interior angles is 1260. So how do we solve that? Yeah, you could do that. You could just show 1260 divided by 180, and that would be 7. But we know that that's short of the number of sides it should be. It should be plus 2. It should be 9 sides. So we need a nonagon out of this. So we need to draw a nonagon on our lattice work here. Got to have 9 sides. It doesn't matter if it's concave or convex out of this. So there really are no rules to that. It's just got to have 9 sides. Doesn't matter if any of the sides are the same length or anything. So just start making yourself a 9-sided figure. So you might, I'm going to start with this. Oops, didn't line up my. So there's my first side. There's side number 2. Side number 3. Side number 4. Side number 5. 6. 7. 8. 9. Be creative. Make it your own. No, as long as it doesn't cross over itself. Yeah, you could do that. I drew a different one when I was making out my notes. I just started new this time. That one kind of looks like a house with a yard thing. I just drew that one for giggles. Okay, so it doesn't matter what it looks like there because it said it didn't matter if it's convex or concave. If it said it had to be convex, then you got special things to do with that. You can't cave it into itself. So be careful of that on that. All right, last thing is the Pentominoes and Tangrams. Okay, I'm gonna be honest, there's not a lot of teaching that can happen with me on this. One thing, we're out of time. The other reason is it's really spatial sense, and it takes just playing with them. Okay, so the box that you got yourself a pentomino box. So we're going to introduce you to the pentominoes. They have names and their letters. Each shape has a letter that it's associated with out of that. So you look at the sheet that I gave you on the Pentominoes that you got, and the first picture there is the F. So the F shape is that one. And it kind of, you squint your eyes, it looks kind of like an F, right? And then the second one is the L. L is that one. Why are they called Pentominoes? P-E-N-T-A. There's 5 blocks in every figure. That's why they're called Pentominoes, okay? Did y'all ever play Tetris? Okay, so you get the idea of filling in this box with the Tetris pieces. That's what you're doing with Pentominoes. And what this is, the standards that this relates to is early elementary kid, it's spatial sense and area and reflecting figures. Because you can, when you go to lay these Pentominoes into this picture, you can lay them in this way, or if I reflect it, if you get into higher level geometry, reflecting it would be flipping it this way, right? Or if I reflect it another way, that would be flipping it down, right? So those reflections are what allow you to put it in different areas out of that. So the idea here is to draw in the shapes that you use to make this picture fill in. So for this one, there's more than one answer to some of these, or to most of these actually. The one I used the P. The W. I'm going to use a different color for the W. So there's that W shape. Or maybe if I trace these out, that helps. You see it. And then the P is right here. And then I'm going to use the Y shape, which is this one, to fill in that gap. And then the last one, I used the I. So the ones that I used were I, Y, W, and P. So I'm just listing the pieces that I used to fill that. That's not the only answer to that puzzle. There are other ones that work. That's the one that I did today.
Are these, we have these in our kit that we want?
No, you do not have these in your kit. That's why I printed you 2 copies of that, so you can cut one out of there. Or if you will promise to bring this Tupperware back with these, you can take these home with you and just please bring them back because they're Dr. Swan's. She'll fire me, and I won't ever get to teach this again. Maybe one of you keep them. No, I'm just kidding. But this is not the only answer. There's other ways to get there. When you go to number 2, it's a different picture, the same idea. Fill it in using the Pentomino shapes, and you're just filling it in there with the Pentominoes. And then when you get to number 3, it tells you which shapes to use. So you're going to have to use an L, a W, a U, the Y, the F, the T, N, and V. You're going to use those shapes, and you're going to be able to fill this complete grid. No empty spots. So it tells you which ones to use. You just got to figure out which way to put them in there. Okay? And then you just draw in and color it with those. This one tells you you're only using L, P, Z, W, and Y. And you're filling in this rectangular shape here. It just takes practice. Now, the tangrams you actually do have in that backpack. They're a little foam set, and I brought mine in with me today. There's actually more than one set that you got in there. They look like this. It looks like a little square out of there. But when you open up one of those little packets, there's a bunch of stuff in there. It's all the shapes of the tangrams. You got the 2 big triangles, the medium triangle, the 2 small triangles, the square, and the parallelogram. If you look at this thing, it's got those same shapes. You got 2 big triangles, 1 medium triangle, 2 small ones, square, parallelogram. I will post this PDF on the Canvas What I had some folks do last year, they didn't like the foam ones because they kind of folded and stuff. And I had some folks last year, or last time I thought this, they printed it out on like cardstock and made it like more of a rigid piece. Or if you just take that and glue it to like a poster board and then cut them out, it makes you a little bit sturdier set. These seem to do okay, but like I said, they're foam. But you got several sets of those in that backpack, and I like this stuff. It's fun. It's puzzles, and my brain needs puzzles to survive. So when you get to the tangram stuff, go ahead and scroll down to that. You're trying to make these shapes, and these should not be gaps. The picture did not copy well. They should be filled in straight lines there. You're trying to make a fish. You're trying to make the house. You're trying to make the dragon or Loch Ness. Nessie there is who you're trying to make there. Using the tangram pieces in whatever way you can to make that picture. And what you do is just take another piece of paper and trace out what pieces you used and made the figure out of it. And it takes trying it. You're going to screw it up a bunch of times before you get it right, unless you're genius level. You guys are smart, but I don't know if anybody else are tangram geniuses. I'm not, but it's fun. Okay. Yeah, you can't use the big triangle. You only have one medium triangle, so you can't use the medium triangle again because you only have one. So you can only use one set to make that picture. That doesn't mean you have to use every piece of that set either, but you can only use each piece one time. Okay. Don't get too frustrated with this. Have some fun with it. Try. Have a little get together and challenge your spouse or your child to see if they can do it. Like I said, you'll get better at this once you pass 12 years old. That's what the research says. So sometimes a fresh set of eyes on it can help. So if you get frustrated with the Pentominoes or the Tangrams, take a break. Come back to it in a day or so. Your brain will have forgotten all the things that you tried that didn't work, and you will get to try all of those things wrong again and maybe stumble into the right one. So if you want to take the Tupperware of Pentominoes with you, you are welcome to do that. But bring those back next week. If you want to make yourself a set of